All right, so gravitational waves, right, are naturally emerging out of Einstein's equations in general relativity. And when you think of that, in 1915, Albert Einstein wrote them down for the first time. And since then, we have understood more and more that, well, they first of all describe the dynamics of the gravitational laws in the large of the universe. And when we talk about solutions of these equations, there's a lot of geometric structure, which is not only, let's say, a mathematical gadget, but these geometric structures have a direct physical meaning. And when we solve the Einstein equations, what we get are the so-called spacetimes, the solutions. And of course, you can do that in various dimensions, but today I'm going to talk about 3 space and 1 time dimension, so 4-dimensional spacetimes. Therefore, gravitational waves, we'll see how are they produced, how do they propagate, how do we detect them. And so there's a lot of, let's say, theoretical knowledge about that, and there have been observations. I mean, the big breakthrough happened in 2015, where LIGO for the first time observed gravitational waves originating from a binary black hole merger. So 2 black holes spiral in, merge, and send out energy in terms of gravitational waves. So we'll understand what are these waves also. And since then, Virgo, another detector in Italy, and LIGO here in the US have observed several events, among others also neutron star binary mergers. So this is really the beginning of a new era that we can really observe these gravitational waves. And this is like taking the pulse of the universe, whereas in a telescope, we always have electromagnetic waves of some sort where we look into the universe. So here we can directly, the universe directly tells us what's going on. So there's another interesting feature I'm going to talk about, waves, certain structures, the sources, what this all means within GR, and what are interesting topics that some people are talking about today, or what research in math and in physics looks like concerning this. An interesting topic concerning gravitational waves, though there's a certain feature called the memory effect. I will also address that. So when you think of the gravitational wave packet that typically is a fraction of a second for a binary black hole merger that travels through LIGO, this will all become clear in a talk today. And when it travels through LIGO, it's not only that we see that the space-time is moving, so the test masses are markers in the space-time to really see how this motion happens. And what is predicted also by the general theory of relativity, but has not yet been observed, and we hope that LIGO and other detectors will see soon, is that there's a footprint left by these waves themselves. So when the waves pass any place here where we have the detectors in the universe, there will be a small permanent displacement of the test masses being left behind. So this is something that is in the range of being observed with LIGO, hopefully in the future, and I will say more about that. Okay, so, well, as I said, waves are the topic of today. Waves are all over the place. Of course, we know fluid mechanics, we know waves in, well, I could have plugged in electromagnetic theory, etc. But what I want to say is here we have a nice picture of just from an animation of 2 black holes merging. So when 2 black holes are binaries in that sense, when in GR, they cannot just stay circling around each other forever, like in Newtonian physics this would happen, but in general relativity what you have is that they have to lose energy, they send energy out, and at the very end, so there's a lot of energy sent out in form of gravitational waves, and they merge and form one single black hole. So what I said here, this maybe I will give you let's say a definition, what is a gravitational wave right now, but we'll see more and more also mathematically in a formula what this all means. So the physical content should crystallize out, but I will also give you some nice formula that we can actually put in here. So first of all, what is a gravitational wave? So is anybody in the audience who would like to maybe explain, or maybe just a sentence, what is a gravitational wave?
Well, if anyone else wants to go, I was just gonna say, when you have a massive disturbance in on gravitational proportions, like supermassive black holes are very gravitationally intense objects, and they're combining and circling each other a motion like that ends up actually sending ripples through space-time, which is what gravitational fields are.
Exactly. So these are ripples in space-time. And when you think of these ripples, you will see them in the curvature of your space-time. Of course, you can also, plug in the metric, but the metric is something I can transform away locally. I can always choose the flat metric if I'm on a point on my space-time manifold, but something I cannot transform away, which is invariant, which is has a real physical and mathematical meaning, is the curvature. Wherever I am, if I'm on a sphere at a certain point, there's an intrinsic curvature to that. And when we talk about space-times, there's also an intrinsic curvature. We can actually talk about, well, we will see what the Riemannian curvature is. So there's a notion of this curvature structure in the space-time. And this is ripples in the curvature of the space-time. That's where you cannot erase them there. That's where they travel. And to see that, on the right, on the bottom right-hand side here, you have a Hubble Space Telescope picture. And many of you, maybe all of you, I think, know what that is. And if not, then, well, I will tell you. But this is, of course, we see gravitational lensing. So we see here at this, so we see there's a faraway galaxy that is sending out light. And in the middle, there's a big galaxy that is which it has a lot of gravitational pull, gravitational potential. And the gravitation by the intermediate galaxy is deflecting the light. So these are not straight lines. This is actually geometrically bent. And when you look at that, there are these smeared out positions, these smeared out objects around the center, where you do have the same picture of the same galaxy a few times. And you have these smeared out objects, which actually is the picture of the same galaxy far behind. So we do see curvature in the space-time, even in the universe, when we take a Hubble Space Telescope picture. Now, black holes, as we just said, are merger of black holes is one typical source of gravitational waves. And when we look at our black hole at the center of our galaxy, so we zoom in, so we have some supermassive black hole there. And of course, you knew that this year we got, in physics, the Nobel Prize was awarded to the observational part for the actually finding out, looking at the innermost stars, objects at the galactic center, and look at the dynamics to infer that there must be really a supermassive black hole in the center of the galaxy. So 50% went to that observation and 50% went to theoretical parts of connected to black holes. So this is our black hole somewhere in there, and a typical galaxy has a supermassive black hole or black holes at the center. And what LIGO has observed so far are really huge black holes merging. And here is another beautiful picture and another breakthrough by the Event Horizon Telescope, which is really a connection of, a network of telescopes working together, taking very clear close-up pictures of a black hole, which this one is in the center of M87. They have also observations of our Milky Way galaxy, but these are a little bit harder to work with. All right, so this is a beautiful picture here, another black hole. And well, Einstein, we all know. Let me now introduce you to the Einstein equations. So Albert Einstein in 1915 has wrote down the Einstein equations, and let me explain them briefly here. So the first equation here on the left-hand side, so we have, this is everything I call R here is curvature. So this is what we call the Ricci curvature tensor. So if you think, maybe just to explain briefly, if you think of a sphere, then you have the Gauss curvature. You can, well, a sphere has Gauss curvature, and if you want to generalize this intrinsic curvature to more general manifolds with a lot of structure and curvature, so then you end up with the Riemannian curvature tensor with 4 indices that run from, well, if you are in 4 dimensions, from 1 to 4. If you take the trace of this Riemannian curvature, then you end up with the Ricci curvature. So on the left-hand side, you have the Ricci curvature tensor, G is the metric, and if you take another trace of the Ricci, you end up with the scalar curvature tensor. You think of the left-hand side, there's some curvature there, there's a geometric structure, fine. On the right-hand side, we have the stress energy or energy momentum tensor. So if you are maybe looking at the neutron star, you would like to plug in, well, you would like to model that neutron star. You would also like to plug in an electromagnetic field, etc. So whatever you look at and has to be described by other equations shows up on the right-hand side in this stress energy or energy momentum tensor. Well, let's say if you have an electromagnetic field, then you also have to provide the Maxwell equations. And what you end up solving or investigating is this system of Einstein-Maxwell's equations. Now, you can also ask, well, maybe first let me tell you what we are solving for. So it's a very specific thing. If you think of other partial differential equations, you may have initial data and you let it flow under the equations, if it's hyperbolic or parabolic, that are given, and you would like to know at the later time, so what does my system do? Can I read it off from the initial data and the evolution of the problem? So we think of this as an initial value or Cauchy problem. And the question is, here we are solving for the metric. The metric is the unknown, but whenever we do handle other PDEs, let's say Euler equations in flat space or something like that, then you never have to talk about, let's say, the manifold is just Rn there, or you may want to do something in special relativity, then you have Minkowski space. But the differential structure is always given, and we don't have to build the solution. In general relativity, this is a big difference. We do not have anything given. By solving these equations, we have to build to construct the manifold. There's not even clear the differential structure, etc. So what we do here, we really have to build all that by solving the equations. So with having said that, solutions of these equations are metrics G, which are Lorentzian. You can think of that when you think of Euclidean space like Rn or three-dimensional real space, then you have the natural metric there is just +1 on the diagonal, 0 otherwise. Now, if you go to special relativity in four-dimensional spacetimes, you have, for instance, a -1 on the diagonal and +1 3 times on the remaining diagonal entries. So that would be a Minkowski metric, so -1 +1 +1 +1, and it's flat because when you take a derivative, it disappears. So it's a flat metric, does not generate any curvature. Now, but the Minkowski metric is a special case of a so-called Lorentzian metric. So what I call here Lorentzian metric, you can just think of that as maybe if you know about Riemannian manifolds, let's say if you want to generalize Euclidean geometry, you look at the sphere, you look at manifolds with certain differential structures and curvature. So you can do the same thing with the Minkowski spacetime. Now, if you generalize this Minkowski spacetime with a negative definite metric, you get Lorentzian spacetimes. So it's a spacetime. Think of it like we have space, we let it go in time, but actually GR by itself does not differ between space and time. That's something we plug in. All right. So by looking at these equations, you can also say on the right-hand side, if I just want to observe pure gravitational effects, then I can say I can put the right-hand side to 0, and then we end up with this equation. Takes maybe a line or two to prove that if the right-hand side is 0, then you end up with this equation saying that the Ricci curvature of the full spacetime manifold is 0. So of course, when you take a time, you freeze time, or you take a picture at time t1 of your manifold, which is then there's just a three-dimensional space, there's a lot of structure, and the curvature of that space is not at all 0. It can actually blow up. But it's just the R mu nu, so the Ricci curvature of the full manifold, which is 0, but also the Riemannian curvature, namely the curvature, which is the intrinsic curvature of any Lorentzian manifold, that will not be 0 in general. That is actually can blow up, but we have singularities. Just to maybe say something about black holes, the typical black hole solutions that we know, which are the Schwarzschild solution and the Kerr solution, showing up in a slide or two. So these solutions are, the Schwarzschild solution is spherically symmetric. The so-called Kerr solution is a black hole with spin, that is spinning. And these solutions, for instance, are solutions of this equation, the Einstein vacuum equations. There's nothing else on the right-hand side. And so the Einstein vacuum equations, you can think of maybe asymptotically flat systems, a system that I'm looking at here where there's some curvature generated by interesting mass or energy locally, but far away, there's the next object that does not really interfere. So we look at asymptotically flat systems often for the Einstein vacuum equations. And so all of the Einstein vacuum equations have a lot of interesting structures and, well, solutions for that matter. So solutions to these equations are spacetimes. As I said, we talk about four-dimensional spacetime manifolds. And so there's no other structure there. So the structure of this manifold mathematically is all there is. Matter, energy, everything that we do and think about is part of this manifold and gives it a structure. So that's basically one of on the level of pictures. We'll have some formulas in a moment, but in Newtonian gravity, you can take Newtonian physics even and put it together with special relativity. In that case, we still have in special relativity, there is time and space unified, but you still have gravitation as something separate, right? So on the left-hand side, you have Newtonian physics. On the right-hand side, what Einstein or general relativity does, it says everything, matter, energy, anything, is part of your space-time manifold. It's not just passive, it's actively changing that manifold. Like what I have here is the Earth is changing the curvature around it. And you see by changing the curvature of your space-time structures, then when you send out light, for instance, it's not going to go on a straight line like in Newton's case, but it has this now different geodesics and curves that are dictated by how much mass and energy there is in the space-time. So maybe as a side note, if you look at this, the Earth is bending, warping the space-time around itself. So for the GPS satellites, for instance, for GPS, to make this really work, you have to take into account that the general relativistic change of the space-time has to be taken into account. Otherwise, the GPS would not work. So this is already affecting GPS, for instance. Great. So here we see another meaning of curvature. And here is, well, maybe let me say a few words also about black holes, because as sources of gravitational waves, we have typically, there's other things too, but binary black holes or neutron stars merging. Now, the Einstein equations, well, have singularities depending on the questions we ask. We put in initial data for the Einstein equations. I still have to tell you how. When you look at the equation, I think it's not obvious at all how this will happen. Took people more than, well, 20 years to figure that out. And so, but I want to say something about singularities first. So the black hole, what is a black hole? Maybe somebody else would like to tell that first. What is a black hole? Everybody knows, but how do we describe it? Well, so if you think of a black hole, well, as a region in space-time where the gravitation is so strong that nothing can escape a certain region. And typically the region, the boundary, it's not really a boundary, but if you think of it as the boundary of that region called event horizon, so when you cross that event horizon from the outside, you cannot go back. So there's some natural, let's say, surface called the event horizon where inside the black hole, certain laws change, but it's interesting mathematically. For instance, you can show that when you cross the black hole event horizon, first of all, not much happens, but for you, well, I think it's not healthy to do that in practical terms, but at least mathematically and physically, there's not too much happening. You still have a nice solution. You can extend the solution to Einstein's equations over the black hole event horizon. The event horizon is no singularity at all. The singularity sits at the center. And this is a picture of that, the curvature blowing up towards the center. Actually, other things go wrong too. So here, first of all, let me present you the people who derived these solutions. Karl Schwarzschild found the first black hole solution, the Schwarzschild solution, which is static and I mean, spherically symmetric. And Roy Kerr found the so-called Kerr solution of rotating black holes. Now, if you think of the rotating black hole, something interesting is happening also when you cross the event horizon. So you can mathematically prove that, well, for the first part, you can still extend your metric over the event horizon in a certain way, but, well, in a C0 way, but not C1. So you don't have derivatives anymore that behave nicely. But within the event horizon, you hit something else, another horizon, which is called the Cauchy horizon. And after that, something weird happens. So after this Cauchy horizon, it breaks. So after the Cauchy horizon, there is the predictability that breaks down, or the causality. So when you think for every nice, let's say, let's say, problem you would like to solve, if I have a system that is causal, like in GR, it should be. So when I'm at a certain space-time point, what I do here, what I have here, depends on the cone backwards in time. So I have a domain of dependence, or domain, right? So my domain of dependence, because these are, I will show you in a moment that this can be written as hyperbolic equations. So I have a domain of dependence on which what I have here, the situation, the condition of the system depends. But when I cross the Cauchy horizon, this falls completely apart. So things do not depend on you anymore. So what happens in the future, so to say, does not depend on what happened before. Causality breaks down. That's, by the way, another way of describing singularities in relativity. This is something which is not so trivial as it might look like. Of course, we know that curvature blows up at the center of a black hole, but there are other things that are weird. So for instance, causality breaking down is something really not good. So it's another way of characterizing a real singularity. All right, so sources of gravitational waves, there's a lot more to say. Typically black hole mergers, neutron stars that merge, or you have a black hole and a neutron star, etc. So these are typical sources. What you also expect to see are gravitational waves from core collapse supernovae. So whenever you have a huge event in space-time that is not spherically symmetric, that is sending out a lot of energy, this will produce gravitational waves. Of course, you can also say, well, when stars merge, this happens too, but they will be really very small. So when I see Cauchy, that's a French mathematician, and this is when I see Cauchy problem, I mean the initial value problem. What are questions we can ask? And let me maybe tell you a little bit of the structures of these spacetimes and extract then what we can learn about gravitational waves from that. So when we talk about these Einstein equations, I showed you, well, the pictures of, let's say, when you have a spherical symmetric solution of the Einstein equations would be the Schwarzschild black hole solution. But these are only, let's say, simple. It's a great solution, but it's a simple and one solution only. What can we do with one solution in general? So not much. So to have an exact solution is a great starting point for research, but what we want to do is much more. We want to know the dynamics of the field. You may have certain systems with certain data. I plug it into initial data for the equations, let it flow, and then I want to see what happens. Will there be no black hole formed? Will there be black hole formation, etc.? This kind of things. So with other words, I want to understand the dynamics of the gravitational field. In order for us to do that at all, we don't look at single solutions. We need to look at a whole set of solutions. So we have, let's say, a set of initial data with certain property, and then we create this set of spacetimes with certain properties. And only then we can actually see how the dynamics look like and extract a lot of information also for gravitational waves. Okay, so let me maybe go on here. So what is that? Let me show you maybe a few formulas here. Let me explain what we have here. The first equation on the left-hand side, this R bar, that's going to be the scalar curvature of a space-like slice. And when I want to give initial data, I have to tell you still what I have to do with these Einstein equations, because when I look at them, there should be a second-order hyperbolic partial differential equation that is nonlinear for the metric sitting there. And I'll show you then in a moment that this can be derived. So we do have actually a second order hyperbolic partial differential equation, so PD. And the Einstein equations decouple into a set of equations for the initial data and evolution equations. So here, we cannot just freely specify initial data. The initial data already has to obey a portion of the Einstein equation. And what we have here is already a portion of that, and with the constraint equations that initial data has to satisfy. Initial data will be given by an initial metric on a three-dimensional space. I'll have it on the next slide or so, and another tensor, and then we have to evolve it in time. So R bar is the scalar curvature of this Riemannian three-dimensional space-like slice. So this, when you freeze t at t equals 0. G bar is the initial metric on the three-dimensional space-like slice. T00 is a component of the stress energy tensor. Lambda, I didn't plug in the cosmological constant. You can also add the cosmological term to the Einstein equations. I'm not going to go deeper into that, but if you have that, then this shows up. And then K and trace of K is going to be the second fundamental form K. So you can think of this as the extrinsic curvature. You have the initial space-like slice, which is a picture of our universe at time t equals 0. You freeze time, you give data there. And when you see how this initial slice is actually curved into the space-time, which is 4-dimensional, when you let the flow start in time, then the K is actually measuring how this initial surface or space of 3-dimensional space is curving into this 4-dimensional space-time. So this is is a derivative at the level of one derivative of the metric. So, and then the second equation here is a law that connects also this tensor K to the stress energy. If you do not have stress energy, then this is just 0. If you don't have the lambda, the cosmological case, then this is just 0. And we are in the Einstein vacuum situation. So these are constraint equations for the initial data. Now I said initial data, I have an initial metric G bar, which is giving me, so if I want to do that in practice, I look out maybe to astrophysical data and I translate what I find, let's say at a certain time t0, into a metric and another curvature component. So G bar is the initial metric, Riemannian metric on this three-dimensional space-like slice, and K, we'll see that is the so-called second fundamental form with respect to time. So with other words, this gives you the curvature, how this initial space-like slice curves into the space-time manifold. Now, another portion of the Einstein equation gives me an evolution of this initial metric and this initial tensor K with time. On the right-hand side, what you call here phi, that's a function that measures how I go from one space-like slice to the next. And Lx, so this is going to be the Lie derivative with respect to a vector field x, and this vector field x is giving a shift vector. If I think of moving in time, so when I move in time from one space-like slice to the next, I can have a certain velocity, and I can actually move towards a different space-like point, right? So phi is measuring what happens along the time vector field, and x is measuring how much I go away from my own original position. So this is that. Now, these equations don't look hyperbolic to me because, I mean, I have a time derivative on the left-hand side, but I told you these Einstein equations are hyperbolic equations. Let me say maybe a few more words in the next few slides. So again, what we want to do, we have initial data. I take, let's say, data from astrophysics. I translate that into some mathematical data, which give me the space-like slice, three-dimensional space-like slice at time t equals 0. And then I let it evolve under the Einstein equations. And the Einstein equations decouple into a set of constraint equations for the initial data and a set of evolution equations that we just saw how to evolve this initial data. Now, questions we can ask, well, do we have stability or singularity? So what happens under different circumstances? By the way, there's also other type of weird singularities called naked singularities. If you do not have a typical singularity is hidden behind a black hole or event horizon, but there are mathematically these other types of singularities of which it's not clear yet if they exist actually in real physics. All right, so here is a mathematical way of saying what I just described. When you look at an initial data set, this is a three-dimensional manifold. You can just think of this as three space. The time is t equals 0, freeze time. Take a picture, that's the initial data space-like, the initial spatial part. And then we have a metric, which is a Riemannian metric, complete Riemannian metric. And this symmetric 2 tensor K again measures how this initial space-like slice H curves into its gonna be space-time. And we also need, if we prescribe matter fields, we also need equations for the matter fields. So what I call here a Cauchy development, so this should just be another name for spacetime. That's our solution. We evolve the data, and what we want to get out of it is a four-dimensional spacetime with a Lorentzian metric. So maybe I'm going to talk here about, I'll say a few more words at the end about cosmology, but in general, I want to look at non-cosmological questions, like if I have a binary black hole system, then I treat that as an asymptotically flat set, meaning I have a lot is going on. I have singularities maybe locally and a large data, but then far away, the data decays towards flat Minkowski spacetime. So there are certain decay rates of the metric and the curvature components to flat Minkowski space, because we can think of the next, let's say, big system is going to be very far away so that they don't interfere. If I want to say something about, let's say, binary black hole merger or a galaxy and check if this is going to, if it does not have a black hole, will a black hole form later, etc. So I treat that as an asymptotically flat system. That's in GR, we have two really big sets of questions. One is cosmological, when you want to answer the question for the whole universe and the history of the universe. And the other one is asymptotically flat, meaning you look at systems like galaxies, black holes, etc. So this is Yvonne Jocquet-Brouillard. So she is a pioneer in general relativity, and she proved the following two theorems. So I'm going to leverage here a little bit. I'm not going to go into the deepest math details, but I want to show you the beauty of the hyperbolic equations at least a little bit. So here is what she did. So you think she was the one to really take the Einstein equations and really write down initial value problem. So a lot of people have jumped onto these equations, physicists, mathematicians, because they thought it is great. In the pioneering years, 1915 up to 52, a lot of people have tried or have worked on it and have obtained partial results setting up an initial value problem, because when you think of the Einstein equation with the curvature on the left-hand side and either zero or stress energy on the right, it's not clear at all how you work with these. It's some curvature components, yeah, now what? So a lot of people have worked on that, and Yvonne Jocquet-Brouillard, she actually in 1952 had a breakthrough result on which anything you do in terms of evolution builds on today. So she showed that if you have initial data, remember H is my three-dimensional space, G bar and K are the data that I give their metric and this curvature, basically second fundamental form here, that satisfies the Einstein vacuum equations, the constraint equations. Then she showed that there exists a space-time mathematically, right, four-dimensional Lorentzian manifold, satisfying the Einstein equations where H embeds into M as a space-like surface where G bar and K are the so-called metric first and second fundamental form. So this, in other terms, it says we have initial data, space-like, and I can actually extend that by solving the Einstein equations into a space-time manifold. Later on with Chirac, she showed that this is actually, there exists a unique globally hyperbolic maximal space-time fulfilling these conditions. What this means is really, now here we have to maybe go to the wave equations as if you look at the wave equation, then you see in wave equation you have the domain of dependence, right? What I said before, if you are at the space-time point, at a certain point in space and time, what I have here could be fluid equations or whatever, depends on the cone towards the past, right? So this depends on the mantle of it. So what I say here is that things happening in GR, what she showed is that you have a well-posed problem. It could be that an equation or a set of equation actually does not make sense at all, and that whatever you construct later on does not depend on the initial data, then this is really physically not a problem we can work with, or it does not even have any meaning. So she showed not only that it has physical meaning, but that you can work with that. So here is maybe the only place where I go into hyperbolic maybe details, but I want to show you that just briefly. So she used wave coordinates, and what she did in the proof is very enlightening in terms of what type of problems these are. So what she has here, what I have boxed, the box is the wave operator, the box operator, the wave operator, right? You have two partial derivatives with respect to time, and then minus the Laplacian with respect to space. But now you think of this is of course in with some geometry. So this is in Lorentzian space-time. So you have some with respect to a metric g. So but think of this as the wave operator. And so now this is equivalent to some conditions that some geometric objects have to fulfill. But the only thing I would like you to remember from this slide is the form of the equation down here. Namely, you have the box, so the wave operator acting on the metric, and that's the space-time metric. And on the right-hand side, I have something, I don't need to write down the details, but I have something, I have terms which are non-linear, better to say, they are quasi-linear in the metric. So they are non-linear. And so what we have here, you can write down the Einstein equations in the wave coordinates as a wave equation of non-linear type. So here is, I'm not going to show you how this is done, but in the proof, one big thing is that from these Einstein equations that look maybe a little bit like encoded when you look at the curvature, Ivan Roque-Brouillard derived a hyperbolic system of equations, meaning you have basically the wave equation, which is nonlinear. I mean, wave equation in these nice coordinates, generally what you have, this is a system of nonlinear hyperbolic equations, so second order. Okay, I don't want to go too much into that detail, but let me maybe say, when we look at the space-time, I want to introduce light cones. We know what light cones are from Minkowski space or special relativity, but if you have, let's say here, what I call sigma 0 and S 0 locally at some, let's say I look locally what's happening, I may have black holes sitting here, and then I send out light or gravitational waves. They travel at the speed of light. They will travel along such light cones. So now in general relativity, these light cones have a lot of curvature structure. So these are light cones as they would look like in special relativity, just for the purpose of keeping things simple. You should think of these light cones as having a lot of curvature structure. They are not so neat, but they have curvature structure. But the same idea holds as in special relativity. I send out light, it travels along the light cones. We ourselves travel within the light cones. And again, this is analogous to the wave equation. We cannot travel faster than light. That would be outside the light cones. Anything we do, information flows within the light cone or on the light cone. So I will use these light cone structures because when we think of gravitational waves, here is the next picture. So when we have two black holes colliding, let's say, then the source is moving along so-called time-like curves. So anything else in the world, we are not at the speed of light, but the black holes themselves and whatever merges there moves at some speed in time. And so the source is moving up in time, but at the same time, at the last, let's say, period of merger, and just when the merger happens, this source is sending out the gravitational waves, these ripples in spacetimes. And here is maybe another picture. The source is moving along this time-like setting, but it's sending out gravitational waves here along which these gravitational waves travel along this null hypersurfaces is another word, or these light cones. Let me just say light cone. You should think of this as a generalized object, but it's still the same in terms of what it does. So the source moves along this trajectory at finite speed, of course, and much slower than speed of light, but at the speed of light, there's gravitational waves sent out. And this picture on the right here with the green source and the light or gravitational wave sent out, I call here something I plus. So the script I plus, this is what we call future null infinity in general relativity. So what is that? So this is where we are sitting on observing. So when we think of LIGO or ourselves doing experiments, we are here at what is called I plus. This means we are far away from the source where the gravitational wave has traveled a long time and distance to arrive where we are. And when we do gravitational wave experiments, we take the data exactly here, far away from the source. We call this null infinity because we are far away. And there's a mathematical concept for that. But when we are here, so what we do, we look backwards in time along these light cones, basically, and we want to understand, decode the information in a gravitational wave about their sources. So this is the picture to keep in mind. And Now, gravitational waves, we have seen, these are ripples in space-time, and I would like to think of them as it's a change or a fluctuation of the curvature. So we see that if you think of a sphere that has obvious curvature or some curved object. So, and now it's not that this curvature stays the same, but suddenly when a gravitational wave comes through, the curvature itself of the space-time is fluctuating. So for a fraction of a second, there's a fluctuation and the wave propagates. And again, I would like you to keep this picture in mind where the source is moving and it's sending out gravitational waves. So what is that picture all about? Let's see, I have here a surface, and of course we think of four-dimensional spacetimes, but let me actually compress a few spatial dimensions. And so there's a surface where the surface should be just thought of as at the constant time t. At the constant time t, I have some surface, and then this curve, so these are straight, these are world lines, ourselves, a black hole, whatever we look at is moving in time. If I don't move around in space, then I'm just moving on this in time on this space-time curve. Now, mathematically, there are relations how these curves or different places in the space-time, how they are related to each other. There's curvature managing the distance between two nearby curves. And when the curvature now changes or a wave comes through, then the distance will change between nearby curves. And now when you think of LIGO, LIGO puts, so to say, a marker on such a space-time curve and tracks then what that actually does. Let's think about this for a little minute. So this is just, I come back to LIGO more closely in a moment, but we can think of this as looking at LIGO from above. So there are three test masses, and they are sitting on each on such a curve that, I mean, we call it a geodesic in space-time, but the curve, if I don't put in any other forces, so then we are freely falling on these space-time curves. And here are just three test masses. And what LIGO has observed already is, so they measure by laser interferometry the interference, the change of these distances. And you can show that the space-time is already changing, and by laser interferometry you can measure the distance and we'll see what happens. But now an important thing is, I just said curvature, the Riemannian curvature is governing how do we actually, we need an equation and something, when we have an experiment, we need to interpret that and we need to tell the experimentalist what to look for, what does it mean? So mathematically, and that's really a beautiful equation. So there's something called the geodesic equation in geometry that governs the equation, the distance between nearby geodesics or nearby test masses now here. And the Riemannian curvature tells me what are the forces here in between that. So interesting enough, the metric I can transform away, and the so-called Christoffel symbols, that's another object that I can compute out of the metric. I can transform away at the point, but I cannot transform away the curvature. That's an intrinsic real physical object. So there is, when you look at that, so what is governed through by the Riemannian curvature tensor is really the field, is what happens between these geodesics or between these test masses. And we can think of this, that the variations of the gravitational field, so the field strength in terms of curvature, this is really described by the Riemann tensor, so the Riemann curvature tensor. So then if you look at the next, well, here is maybe, this is the equation that LIGO bases on. Here, there's a lot, when you go into details, there's a lot of beautiful mathematical structures, but it can also be very involved if you dig deeper in. But in the end, for the asymptotic, let's say, description of the gravitational waves, it simplifies a lot. We need to dig into the details, but we can then extract a beautiful, simple picture at null infinity. So what does number 8 say? So I told you about these geodesic equations, or when we want to see how these test masses are changing with respect to each other. And again, test masses are just a marker. They don't do anything. They are marked to tell us that the space-time, where in space-time am I looking at and what is the space-time doing? And I can think of this as these nearby curves or geodesics. Now, when we are close by on Earth, then I can take the geodesic equation and replace it by the so-called Jacobi equation. And you may have seen that under the name geodesic deviation equation. So what we have here on the left-hand side, you can think of this. So this is, you can think of the left-hand side, there is some let's say, spatial difference I would like to look at. There are two derivatives of the spatial coordinates, if you like. So there's a delta x sitting in there. So I want to measure the change in space. And so I have two derivatives. You can think of it as an acceleration. On the right-hand side, I have the curvature. And so basically I have a delta x, or the change in the space in the test masses, how they move, is governed by the Riemann curvature tensor. I can think of it, I have two derivatives in time, which is governed by the Riemann curvature tensor. Now, technically, if I know by investigating the Einstein equations for certain type of data, and I go out to null infinity, that's where I travel with the waves far away, and I try to see how asymptotically this solution behaves, then this Riemann curvature tensor encodes a lot of information. And when we can really solve the equations, we dig deeper into the structures, we get the information out, and then we see what we can read off or predict and interpret about the source when we're sitting away from the source at this I+. So this is the Riemann curvature tensor. And again, in a four-dimensional space-time manifold, the solution of the Einstein equation, the trace of this will be zero in the Einstein vacuum case, but this is the actual Riemann tensor. It's not going to be zero. This has a lot of structure. So if we are in the pure gravitation case, where the right-hand side is zero in the Einstein equations, meaning we have just the pure gravitational case, no stress energy, then this R is what we call, it has a name called wild curvature. So it has a certain portion of the curvature which describes the pure gravitation without any stress energy. If we couple the Einstein equations, for instance, to an electromagnetic field or any other matter, then this Riemann curvature has other components that come in through the right-hand side of the Einstein equations, which are the stress energy tensor. So if we are not in vacuum, then the stress energy tensor also enters this curvature. But you have actually a non-zero curvature that actually blows up for singularities or black hole solutions, which is given by the wild curvature when there is pure gravitation. Okay, curvature tells us how this stuff moves. Now, what does it mean? So again, this is just another way of looking at curvature. Maybe I just jump here. So now let's go back to the LIGO experiment and just think briefly how this actually works. Now, here is again this three test masses on the right-hand side. So you have a test mass in the middle, one to the right and one to up on the screen. So it's like L-shaped. And so then they send it laser light. So by laser interferometry, you can measure now any change of the test mass. So the test mass, so in reality here on Earth, you have mirrors suspended by pendulums. And so you have a free motion in the corresponding plane then. So when now a wave train comes in, what happens is, oh, here is, by the way, a LIGO picture. That's the facility. There are two of them, one in Washington State, one in Louisiana. That one is in Livingston, Louisiana. And you can see this L shape. These are these long arms that we see here, where the laser light is going back and forth between these three different test masses or mirrors. Before I go deeper into the details, of course, there was the Nobel Prize awarded also for LIGO. So that went to Ray Weiss, Barry Barish, and Kip Thorne in 2017 for their work of observing for the first time gravitational waves that was done that they really found for the first time in September 2015. And now there's Virgo, there's other observation facilities being built. So again, there's a lot more that will happen in the future. And I think it's an absolutely great breakthrough. Okay, so maybe something to say for the sensitivity. Okay, that comes up in the next slide. But maybe just very briefly in words, if you think of the sensitivity, if you look at the field strength that they have observed already. So if you look at, let's say in physical terms, if you take the delta lambda over lambda, so that's at the order of 10 to the minus 21. That's what they have seen already. Okay, here maybe a little bit of data. So what kind of frequency and etc. do you expect? So LIGO and ground-based detectors are are mostly detecting gravitational waves from sources of binary black holes, binary neutron star mergers. There is another project, there's many more to be built and to go online on Earth. There's the so-called LISA detector going up to space, hopefully soon. So that is even in a little bit different frequency range. So here you could actually measure really massive black hole mergers, stellar mass compact binaries. This pulsar timing array, oh yeah, I should mention that. Pulsar timing array is already going on. This is radio astronomy that is used, so radio telescopes. And so this is something you need to take. Here we look, instead of looking at that, the setup is different. Here we look at pulsars. Pulsars are really great clocks for us in terms of very precise in their period. When we look at the signal from pulsars and gravitational waves are coming through while we are obtaining signals from pulsars, we would see a shift in the frequency. So that's another thing. And also in the cosmic microwave background, we hope to see footprints of primordial gravitational waves. So there's a lot more to come and happening at this point. So let me say maybe, okay, let's see how much time. Do I have another 5 or 10 minutes, by the way?
Yes, of course.
Okay, thank you. So 5 or, yeah, less than 10. So I should finish soon. So now we look again, but at the schematic picture of LIGO. Let's see. So again, so these mirrors, these are these 3 test masses. And what LIGO has seen already, point 1 here is what I call instantaneous displacement of the test masses. So when a wave packet travels through, then we have all seen probably this spectrum, and this is changing. So we see instantaneous displacement for a fraction of a second, and then they go back to rest. So that's what they have observed already. And now I want to mention something else. There's something called a permanent displacement of test masses. They have not yet seen that, but when I talk to people at LIGO, they're very hopeful. They have it on the to-do list already, and they want to know more what we can do with it afterwards. So we hope that they will observe that in the near future. So that's the so-called memory effect. So what is that? Now, what I have here as, this is with these arrows. So in what you would expect if there's no memory, that these test masses go back to rest where they were before, right? So no display. So there's a wave coming through, they move, they go back to where they were before. This is not what will happen. So general relativity predicts that they will have a permanent change, like I have in this picture, like let's say and so here, when you have 3 test masses, you can look at the reference displacement among them. So test mass 1 will be permanently displaced like this arrow, and test mass 2 like this arrow. So this is of course too much. The delta lambda over lambda, the field strength for something like that would be 10 to the minus 22, just a tiny bit more than what LIGO has seen already. However, here on Earth, this is actually a very low frequency effect, and on Earth we need to filter out this noise. Anyway, so this is a prediction of the gravitational waves, that there are 2 types of this memory. Here, the first type of this memory was found first mathematically in 1974 by Seldovich and Polnareff, and then in the fully nonlinear regime by Dimitri Christodoulou in 1991. And so what this effect says, as I just said, is that after the wave packet travels through, there will be a footprint, there will be a permanent change of the space-time that will be visible as a permanent displacement of the test masses. And I don't want to go too deep into all these structures. There's a lot of beautiful, let's say, new work that we found new structures, but interesting enough, these works by Seldovich and Polnareff and Christodoulou. So I had some work with my collaborator, David Garfinkel, and we found that these 2 effects are actually not the same. They do the same, but these are 2 different types of memory effects. So there has been a lot of work from the early day on, and recently in the last few years, there has been a lot of more people coming up with new works. And recently in the last few years, there has been, I think, a couple of papers by Lasky, Thrain, Levin, Blackman, and Jen, who work part of the LIGO collaboration, suggesting how to detect memory from LIGO by stacking events, actually. So, I mean, to this memory effect, there is a lot, maybe I go on, there's a lot more which is contributing to this memory effect. If you have, let's say, 2 neutron stars merging, there will also be a lot of electromagnetic waves going away. And this electromagnetic structure also, of course, causes curvature. And we have shown in various collaborations that, first of all, electromagnetic waves add to this structure, that neutrino radiation increases this structure. For the first time, actually, outside of GR, David Garfinkel and I found analogies in the pure Maxwell equations without gravity. There are two different types of memory actually there. So recently there has been a lot of search for memory analogs in other fields by Strominger and collaborators and many more people, but I'm not going to go into that now. So back to our displacement. I have maybe 2 more minutes to finish here. So we saw the setup of LIGO, and I showed you the so-called Jacobi equation. Remember, where we had 2 derivatives of x on the left-hand side and the curvature term, the Riemannian curvature, on the right. Now, when we do these 2 integrations, we cannot just integrate and everything is fine. We have to take into account what we find by studying the solutions of the Einstein equations. But when we do that, so from this equation that I showed you, by investigating the Einstein equations, we put in the information for this curvature term. We know more about how certain systems look like far away from their source, and put that also into this equation that I showed you before. And when we do that, we end up with this thing, which is that a delta x on the left-hand side. So this is now a change. And if you think of the pictures from before, this is how it's the permanent change of these test masses. And if I don't go out all the way up to, I have here the d0 over r, forget about that. It's just a constant. This depends on the initial space-like separation of the masses. But what I have here, sigma plus minus sigma minus, that's an object. You can think of that. That's an object I measure at null infinity. And now I'm at null infinity, far away from the source. What happens really so when a wave train comes in, I integrate, I follow this wave train and I integrate the wave train far away from the source to see what does it do to my test masses. And when I do that, if I do not go up all the way to, this is what I integrate over what is called retarded time, for those who know what that is. Otherwise, let me say there's a parameter, there's a function at null infinity, and I integrate over that function, which is basically summing up over all the light cones that reach null infinity. You think I shoot out the light now, then it will stay on one light cone and reach null infinity, and I register it there in LIGO. A little later, I get another light or a gravitational wave sent out, and it will be registered at another light cone at null infinity. And here I'm summing or integrating over all these light cones at null infinity, far away from the source. So on the right-hand side, there's a lot of know-how and investigations that goes into that, but it tells me this right-hand side has the information it tells me what LIGO saw already. If I don't add up, integrate up to all over null infinity, but just keep sitting on the wave, basically, then I get on the left-hand side what LIGO observed already. If I integrate out over all the light cones at null infinity, then I will get the memory effect that hopefully they will see soon. Maybe the last minute, okay, in this, maybe I jump here to one of the last slides, maybe just to tell you here. So what I just said, right, in this right-hand side of this equation, here it is again under a different name. So what LIGO has measured already is when U is my retarded time, that's one specific light cone at null infinity is labeled U. And if I integrate up to a certain time, then I get the displacements that LIGO has seen. If I integrate over all of those light cones, then I do get this memory effect, which is a permanent change of the space-time. And interesting enough, this is sourced by energy radiated away. I call this F down here at the bottom of the slide, this psi squared. This is the energy of the pure gravitational wave. Just the wave itself is radiating, and that's radiated away. The AF, this is if I plug in an electromagnetic field, for instance, so that would be the portion from the electromagnetic field adding to that memory effect. So there are 2 types of memory adding to that displacement. And maybe I jump to the last slide. I think I skipped the cosmological part. So I think what we have seen here, maybe just the hint of ideas I would like to I would like you to remember, there's a lot of beautiful structures in gravitational waves. The way we look at them, we go deeper into these Einstein equations, see what the geometry does, and interpret what does it mean physically, what physical meaning does it have. And when we look at these waves, in LIGO, for instance, by investigating these types of initial data, let them flow under the Einstein equations, it tells us what kind of radiation patterns does occur at null infinity and what can we learn about the sources. So maybe I'll stop here and take questions. Thank you for your attention.